Hi there, I'm Martin and I've been working with the team at Great Scott Gadgets on developing Cynthion, which is a new tool for exploring and experimenting with USB. In this video series I'm going to try to show you some of the kinds of cool things you can do with Cynthion, and the end goal is we're going to try to emulate this, the PlayStation 5 controller, and then use that emulated controller to do a tool-assisted speedrun of part of a PlayStation 5 game running on the console. Which is something that right now I don't think anyone's done before. And along the way I'm going to show you all the different ways that you can use Cynthion. So even if you're not that interested in the PS5, this series is going to be a sort of bit of a tutorial that shows you all of the different features of Cynthion and all the different things you can do with it. There are a lot of things you can do with Cynthion. You can use it as a sniffer to capture USB packets going between devices on the wire, like a USB packet analyzer. You can use it to emulate other USB devices, so maybe plug it into a computer and have it pretend to be some other device. Or you can take an existing device, like again maybe this one, and have it sit in between that device and the computer, console, phone, whatever, and modify traffic going back and forth as it's in transit. You can also use Cynthion as a platform to develop your own USB devices, and it's a very capable, versatile platform for doing that. So let me say a bit more about where this comes from. Great Scott Gadgets is a company that designs and manufactures open source hardware tools to help you do things that maybe you couldn't easily do otherwise. And the whole mission of the company is to put powerful open source tools into the hands of innovative people. So Cynthion is the newest product, and this is something that was crowdfunded through Crowd Supply, and we're very grateful to all the people who backed this project and helped make it happen. But that campaign is complete now, and so this is now available off the shelf as part of the regular Great Scott Gadgets product line. So you can go to this page here at greatscottgadgets.com/Cynthion. And there's links there to all of the resellers where you can go and buy this, and all of the other Great Scott Gadgets products, and also to all of the documentation and where to get help. Now the documentation pages will tell you all about how you can get started with using Cynthion. There's some tutorials there, and there's information about the hardware, where to get help, and information for if you're developing new things for this platform. When you receive yours, it will come in a box, something like this, and if we open this up, here is the device. As you can see, it's quite a compact thing. It's in a milled aluminium enclosure. It's anodized and laser engraved. Very slick. We're very pleased with this. It feels really nice. Great work by Timon, who did this mechanical design. And obviously, I'll go right ahead and open this up and show you the board. So inside here, you can see the hardware we have in there. Now, everything to do with this is open source. The hardware, the gateway, the software, everything. So I can go right ahead and show you the board layout here in KiCad, and so also in 3D. This is all based on an FPGA in the middle here, a Lattice ECP5, which is one of the FPGAs for which there's now a fully open source toolchain, which makes it really nice to develop for. We've got 4 USB ports that can be used for different things. All of these have power switching, voltage and current monitoring. We've got Type-C controllers on 2 of them so that you can do power delivery negotiation and things like that. We've got some extra RAM on there. We've got a little microcontroller that manages the FPGA. And we've got these 2 PMOD ports at the bottom, so you can take all sorts of off-the-shelf boards that conform to the PMOD standard to plug in other hardware or connect your own or monitor other signals alongside USB. So this is a very capable platform for all sorts of things. But you don't have to develop anything yourself to use this, because as well as developing all the hardware, we've also written all the software you need for most things that you might want to do with this. So I'm going to start off by showing you how we can use our software to use Cynthion as a packet analyzer, what you might call a sniffer, and we're going to capture USB traffic from this controller while we're using it, and then we'll look at how that data is structured. We're going to look at how the USB protocol works and how different kinds of devices use it. Now, the software for doing capture and packet analysis with Cynthion is called Packetry. This is a brand new application which we wrote from scratch specifically for this project. There's some other tools like Wireshark, but they didn't have all of the performance and the features that we wanted, so this is new. If you follow the links in the Cynthion documentation, they'll take you to this page here on getting started with Packetry. And this will show you how to install it. There's releases for Linux, for macOS, for Windows. You don't need to build anything yourself, it's all ready to go. And then here on the desk, I'm going to show you how to connect Cynthion to use it for packet analysis. So to capture traffic from this controller, we need to connect Cynthion in between the host, the console, and the device, in this case the controller. And we do that using these two ports on the right hand side of Cynthion. These are called the target ports. And these two ports are actually connected to each other internally. So data can flow through Cynthion on its way through between devices. We're not interrupting anything, but as it goes through there, we can sniff that traffic. So I've got one cable running from the PS5 console to the target C port on Cynthion, and then another cable going from the target A port to the controller. And then I've got a third cable which is going from the control port on Cynthion to the machine over here that I'm running Packetry on. Now note, when you buy a Cynthion, it doesn't come with cables because there's so many different types of cables you might need depending what you want to do with it. So if you're getting one, just check the documentation and make sure you pick up whatever cables you're going to need for the devices that you want to play with. Now if you start Packetry, you'll get a screen that looks something like this. So we have some controls at the top. This is where you select the device that you want to capture from, and you can see it's detected that we've got a Cynthion plugged in. And you also select the speed that you want to capture at. Now USB 2 has 3 speeds. They're called low speed, full speed, and high speed. And any given device is only going to use one of these speeds. So you can either try to work out which one it uses, or you can just try capturing at each speed and see which one works. At some point we will be adding automatic speed detection, but there's a few other things that need to happen first to do that. So at the moment that's manual. Now in this case, I already know that this controller is a high-speed device, so this is the right speed to capture at. But there's one other thing we need to do over on the PS5 side. Now, by default, this controller connects to the console over Bluetooth. So in order to sniff it, we first need to make it communicate over USB. And we do that by going to the home screen on the console, and then to Settings, and then in there you'll find a section on Accessories. In there there's a section for the controller, and that is where you'll find this communication method setting. So by default this will be set to use Bluetooth, and if I select the other option, it will use the USB cable. Now this doesn't stop it working as a Bluetooth controller. It just means that if you've got it plugged in, it will send data over USB rather than over Bluetooth when it has that choice. So let's come back out of there. And what I'm going to do is just start off with this controller unplugged, because I want to capture all of the communications with it, right? So over in Packetry, I'm going to press the record button up here, which starts it capturing. And then I'm going to plug the cable in, and immediately we're going to see a whole lot of traffic. So here you can see some of the first things that happen when you connect a USB device. When a device first shows up, it shows up as device 0, and the first thing that has to happen is that the host gives it an address. In this case, it's being given address 1. So this is almost like DHCP on a network. Everything has to be given an address. And then it asks the device for a lot of information about itself, which comes in the form of things called descriptors. So we're getting device descriptors, string descriptors, configuration descriptors, and so on. And there's a lot of that goes on so it can figure out what kind of device it's dealing with. And then later we'll see traffic being transferred, and you can see here that there's sort of ongoing traffic on an endpoint. Now, unlike when you capture with a software USB sniffer going through the operating system, we're capturing every individual packet on the wire here. So if I go into the packet view, you can see every single packet, all time stamped down to the nanosecond. Our timing resolution here is 16 nanoseconds. So this is a very sort of low-level view of the capture, and then Packetry is interpreting this to understand the sort of higher-level requests and transfers that are going on in the protocol. Now, you don't have to understand everything that's happening here. I'm going to show you how you can do some things with this even if you don't understand very much about it at all, because what we care about is just finding which data is interesting to us. But if you want to start learning more about USB, then there's two really good resources that I'd recommend. The first one is this site that's called USB in a Nutshell, and you can find this at beyondlogic.org. And this is just a really good introduction to how USB works. And the other source I'd recommend is the USB standards themselves. You can download all of them for free from usb.org. Some of them are quite big documents, but they're actually quite clearly written. They're not too hard to read. This one here is the main USB 2.0 standard. And then there's a lot of other documents that give more detail about specific things like certain device classes and so on. So this isn't necessarily where I would start reading about USB, but if there's something in particular that you're interested in, don't be afraid to look up the official specs. They're all actually quite accessible. So now that we're able to capture traffic from the controller, I want to start looking at how all the different features of this controller show up on USB. Now, this controller does a lot of things. I mean, it's an input device, it's got the sticks and the buttons, it's got the analog triggers, it has a touchpad here, it has motion sensors, it has haptic feedback, it vibrates, and it's also an audio device. It's got the microphone on the back here, and there's a speaker in it. So it's a really good example of a USB device that does lots of different things, and part of what I want to do in this series is show you how all of that fits together at the USB level. Now, when you get a PS5, it comes with a built-in game called Astro's Playroom, and it starts off with a demo of all the features of the controller. So I'm going to go through this demo because it's a great way of going through all the features of the controller one at a time. And then for each part of the demo, I'm going to capture the data from the controller while I'm using it. So once we've done that, we're going to be able to use those captures to look at how all those different controller features show up in the USB data. So I'm going to stop this first capture here. This was just me connecting the device. And I'm going to save this to a file. We'll just call this connect.pcap. That's the file format for captures. So that's saved. And then in a minute, I'm going to start a new capture. So we're going to go into this controller demo. And this whole sort of built-in demo game is all sort of arranged around like the history of the PlayStation platform, all the different hardware that they've had over the years. It's quite a fun little game. It'll take you a few hours to complete it. It's not very big, but yeah. So first of all, we've got vibration. Yeah, you may have heard that. This thing is vibrating. Um, and then here we are with the first of the controller inputs. So these are the adaptive triggers on the side. So let's start a new capture. We can see a bunch of data coming in. And if I pull one of the triggers, you can see it move on the screen there. And there's a point where it clicks past, and same on the other one. So that's our two triggers. And I'll stop that, and I'll save that as triggers. And then next feature is the touchpad. So this is on the top of the controller here. And again, I'll start a new capture. I'm just going to spell out GSG on the touchpad and stop that and save that. Next. Right. So this is the motion sensing. So I'm going to capture this, and we're going to move this in each axis, and it's making it feel like there's a bunch of little robots rolling around inside. I'll stop that and save that as motion.pcap. And then next we've got the microphone, which is on here, and what it wants you to do here is blow into it, which actually parts of the game use this as an input. So I'm going to blow into this here. Okay. Oh, I didn't record that. Let's do that one more time. Okay. So we'll save that as mic. And then that's it. Okay. So now we've got some data captured. Let's have a look at one of those. I'm going to start with the motion sensors, right? So we've got traffic flowing on a bunch of different endpoints. Endpoints on USB are kind of like ports on TCP/IP networks, in that they're a particular function on the device that data can flow in and out of in a sort of sequence. And there's 4 endpoints involved here. And here we've started the capture while the device was running. We've only really got the data traffic. We haven't got the context of what was going on when the device was connected, which tells us a bit more about what these different endpoints are. So I'm going to come back to the first capture we did, because here we captured all of the descriptors, and that tells us something about the device. Now in Packetry you have this second view that gives us the hierarchy of the descriptors. And so they look something like this. You have for a device, you have a device descriptor, first of all, and that tells you things. That's where you find the vendor ID, the product ID, there's a version, manufacturer and product strings. It basically tells you what is this device. And then devices can have one or more configurations they can be in. In this case there's only one configuration, and that's defined by a configuration descriptor. And then within that configuration it has different interfaces. Now there's several interfaces here, but most of them are audio interfaces. This is defined by their interface class, which is specified in their interface descriptor. And then there's another interface which is a human interface device, and this is where the main sort of controller functionality is found. And within interfaces you can see the endpoints that they're associated with. So the human interface device on here has an endpoint 4 in, endpoint 3 out. And in and out refer to the direction that data is flowing between the host and the device. And it's always relative to the host, because the host is in control of everything. In this case, the host is the console. So endpoint 4 is human interface device data, i.e. controller data, flowing in to the console. So that's where we're going to find our control inputs. And the other endpoints we're going to see are things like data flowing out. This is going to be like our haptic feedback, right? Because this is going out to interface to the human. And then we've got audio flowing as well. Now for the audio interfaces, I'll come back to that later. But right now, we know that we're looking for controller data on endpoint 4. So let's open up our motion one again and look back at the traffic. And here we are. We've got unidentified transfer of this many kilobytes on endpoint 1.4 in, right? So this is our controller data. And we can see all of the bytes being transferred. And what I'm going to do is just take all of that data and save it to a file. So I'm going to call this motion.bin. And then I'm going to have a look at that in Python. Now at this point we have the data that we've saved from that endpoint. It's just binary data. We could look at it with whatever software we like. I'm going to use Python here just because that's what I'm familiar with, but you could use anything. So I'm going to start up IPython, which is a sort of improved Python shell, and I'm going to import the NumPy library, which is a very handy tool for dealing with sort of arrays of data, and I can use that to load the data that we saved as an array. I need to tell it what data type to bring that in as, and I'm just going to bring that in as unsigned bytes. And so that gives me this array of that data, which is 400,000-ish entries long. So we don't have any structure to this at the moment. But let's come back to the capture that we saved this from. This is that data that we've captured. And if we expand this transfer, we can see the individual transactions that make it up. Now, a transaction in USB is a short sequence of packets. So in this case, it's the host saying, do you have some data? The device is saying, yep, here's some data. And the host saying, okay, I got that data. And you can see each of these is coming in a chunk of 64 bytes. And we can see, looking at the data that's in them, we see sort of repeated values from one to the next. So it seems quite plausible that this is data that's coming in with the same sets of values every time, right? So this is structured data where an update is 64 data bytes, and we're going to save the same things in the same fields from one to the next. And looking back at the timings, we can see that these come in a couple of milliseconds apart, right? So this is being polled at something like 500 hertz. Okay, so back in Python, we can now reshape this array. We can ask, okay, let's have that array as something by 64. And now we have a 2D array where the first element is the first 64 bytes and the second is the next 64 bytes, and so on. And at this point, I'm going to bring in another library, matplotlib, which is for plotting data. And a really handy thing we can do with this is just display that data, which is now in a 2D array, as an image. So I can make that figure like that and then display it. And so now we have an image, and it's 64 pixels wide by however many tall, based on how much data we captured. And if we zoom in on part of it, we can start to see some structure in here, right? And we're looking, this was the data we captured whilst moving the thing around to sort of activate the motion sensors, and we'd like to see where that data is stored. And immediately, although there's all sorts of stuff that's changing on a sort of short-term basis going on in here, we can see over here there's a sort of set of bytes that is sort of changing quite a lot, at a sort of speed that might be consistent with that being the motion sensor data. So let's zoom in on a small part of that and have a look more closely at it. Now here, for instance, in this column here, we can see data that's changing quite quickly and repeatedly. That might be the sort of the low byte of a multi-byte value, and then 2 bytes over we've got another that's doing kind of the same thing, and next to them we've got data that's changing more slowly. We've also got this sort of flip here, that might be a sign change. So this is looking to me quite consistent with this being something like sort of 16-bit signed numbers. So let's so here we've got data changing quickly, slowly at sort of column 16 and 17. So let's try plotting the 16th byte of every row of data. And okay, that's sort of all over the place, but if we zoom in on part of it, yeah, we can see there's some curviness to it, but yeah, this definitely seems like it might be like the low byte of something. So what if we take 2 bytes there? Okay, and these are definitely related somehow. So we're going to try viewing that as a 16-bit signed number, and sure enough, there we are. That now looks like something sensible. Now if we come back to the image view that we had, we can see that that was sort of the first of a few fields working similarly. So let's try the next one up. We'll go byte 18 and the next 2 bytes up, and yeah, something similar. So we could plot all of those together. So 16 up to 22, and yeah, okay. So this, I think, is the gyro data from the device, because we were moving it like this, and like this, and as a result you can see the 3 different axes of gyro data, rotating one axis one way and then the other twice, and then the same on the other axis, the one in green, and then the same on the 3rd axis, with a little bit of coupling between them because that wasn't right on the axes. So I think we find the gyro data, and here's a wild guess. If we take the next 6 bytes up in the same way, I reckon we're going to see, yeah, accelerometer data. And This is what accelerometer data looks like. It's quite noisy, and you've got one axis that's always got a value on it because of gravity, essentially. And if you rotate it, then that value shows up on, that offset shows up on one of the other axes or shared between them. So we've gone in not very much time from not knowing anything about this device to now capturing data from it and figuring out where some of the stuff is stored in it. But this isn't actually a mystery how this is stored. The USB Human Interface Device Standard actually specifies how devices report the input data that they generate, and all of that is specified through descriptors. So if we come back to the capture and open up the capture we made when we initially connected, we can see a number of class requests where the host is requesting more information from the device, and some of these are going to contain the HID descriptors, which are going to explain how this device sends its data. But nonetheless, it's quite useful to go through the process of, how would we reverse engineer this if we didn't have that information? Because sometimes you'll be dealing with devices that are, completely proprietary, with their own protocols that aren't documented, or maybe they have some particular features that you don't understand how they work. So these are the sorts of techniques that I use when reverse engineering, and this has given us a sort of bit of an insight. So in the next video, we're going to look at, can we pretend to be this controller? So we're going to use Cynthion in a different way, along with the face dancer library, to make it emulate the controller and see if we can convince the console that that we are in fact this controller. But I think this is a good place to stop for now, and so I'll join you again next time. Thank you.